Okay, let's get started. Hello, everybody, and welcome to this next webinar in the series of SimScale webinars. Today, I'm joined by a couple of guest speakers, which is really exciting, and we're going to be focused on utilizing shape optimization and in conjunction with CFD simulation. I'll introduce that a little bit more in a minute, but first I'd like to introduce who I am. I'm John Wild. I'm VP of Product here at SimScale. I'd next like to introduce Marco. Marco, would you like to say hi and introduce yourself?
Hi guys, my name is Marco Wissinger. I'm a development engineer at Gemu. I've been with the company now for approximately, let's say, 2.5 years, and I'm working in the pre-development department, mostly focusing on CFD simulations.
Thank you, Marco. Mattia?
Yeah, thanks, John. Hi, I'm Mattia. I'm responsible for sales here at Friendship Systems. I've been with the company for approximately 14 years now. I've worked in engineering before moving to sales. And originally, I'm a naval architect, so quite a different discipline, but I've dealt with the optimization of fluid-related geometries, all kinds of geometries for many years now. And I'm happy to be talking here today.
Cool, thank you. Really excited about today. I think I'm meant to be simulation kind of agnostic, but I'm still a CFD guy. I think that will never change, so I'm really excited about today. Awesome. I'm going to turn my video off now. Maybe you want to do the same. And then I've got maybe 3 slides of introduction. And then I'll hand straight over to you guys for the interesting part. So what I'd say really is most of this webinar is not about SimScale. It's more about the valve and the optimization. So 3 slides to begin with about who we are. Our mission, at least, is to empower every engineer and designer to innovate faster by making high-fidelity simulation accessible from everywhere at any scale. And to do that, we've basically put simulation in the cloud behind a browser. So you can access SimScale from anywhere. What we're going to talk about today is the valve that you see on the right-hand side. And we're going to look at how engineers and designers can leverage shape optimization to solve real-world problems with engineering simulation in the cloud. So I've got 2 slides after this talking about SimScale, and then I would hand over to Marco at Gemu. He'll talk about how simulation is useful and how you need insights into how the valve performs to increase its overall performance. Then he'll hand over to Mattia at Friendship Systems, who'll talk about how he leveraged simulation in the cloud to take the original valve design, run hundreds of simulations to produce a final optimum design. Okay, so a tiny bit about who we are. I'd like to give a bit of a comparison between traditional CAE and SimScale. So focusing on us on the right, being browser-based, we have no additional hardware requirements. So there's no additional hardware footprint and really unlimited computing power in the cloud. So you could run all of the designs that we see in the webinar today in one go if you wanted to. So everything, like within an hour, you could have all of those simulations complete. So everything is just there at your disposal. We're cost efficient because we don't require the additional hardware that often HPC simulation offerings do. And we can also offer usage-based pricing. So we're truly a SaaS offering. And we're easy to use. I think this kind of comes in different ways. So simulation is easy to learn, easy to use. But if you find that it's not and you need help, we have world-class and live support. So really excellent structural and fluid engineers online waiting to help if you need support. And you can do that as well through the collaboration that we have. So all projects, our customer projects at least, are all private, and at any point if they want to, they can share them with our support and we can help right in the moment and we can jump into that project. This would also work between engineers and designers in the same company, so you could share projects and collaborate on them at the same time. Okay, so kind of stepping back a little bit to think about the product lifecycle from concept on the left through to full operation on the right. Where we see most simulation software sitting is in the design validation stage. So once the design is fairly ready for production. What we want to do is move towards the left and focus on early stage simulation, which is where you can really start to change the design. It's much harder to do later, but if you do it at the beginning, you can really change the trajectory of the design process. So that we see actually SimScale can sit across both. So we can focus on the early stage, but also the late stage is very accurate. So you can really do both here. And then what we want to do is start spreading out to the left and to the right. And what we're going to do today is start to look at the design space exploration in the concept phase. And to try and give you a better picture of what SimScale does, we do all of the HPC orchestration, all of the infrastructure work behind the scenes. So you just need a simple login. All the licensing, middleware, networking, simulation, storage is all taken care for you in the background. On top of that, we've got different solvers and meshes and the ability to modify the CAD that you brought in to SimScale. And you can leverage this to run different simulations in different applications. So for example, many different structural simulations, thermal simulations, structural or fluid, or purely fluid simulations. And as we're progressing, obviously we're adding more and more solvers, more meshes, and more applications. So SimScale sits at the top, a SaaS application. So software as a service, I kind of think of it as simulation as a service, sitting up there at the top. And all of this can be controlled via the API. Some of that we'll look at today because we didn't set all of these up manually. Obviously, we utilized our API to run all of these simulations. And we also have third parties building on top of SimScale, so building their own interfaces that have access to everything that SimScale can do. And to try to help a little bit today, we're going to focus on these 4 areas. So from the bottom, we're using one CFD solver to focus on an internal flow problem. We're leveraging our API to help us explore a design space. So those are the things we're going to focus on today. And at this point, I would like to hand over to Marco, who will talk to you about the valve and share some details about how simulation can be useful.
Okay, nice. So hello again from me to the audience. I would like to start my presentation with a brief introduction of the company I'm working for. So it's Gemu, because I think Gemu is not that very known to you people listening to this webinar today. Gemu is one of the leading manufacturers when it comes to valves, measurement and control systems. And considering sterile applications, Gemu is here the global market leader when it comes to valves, process and control systems. Today more than 2,000 people are working here at Gemu, and the total group turnover is more than 330 million euro. Of course, Gemu is not only represented on its German sites, which you can see here on the right side of the slide, but in more than 50 countries on all continents, including 26 subsidiaries and 6 production plants worldwide. To give you a more detailed insight into the organizational structure of Gemu, I prepared the following slide. So in general, Gemu is built up of 3 major business units and a smaller business unit, which is called a business segment. And the first business unit I want to mention is the business unit Pharma Food Biotech. And a representative product of this business unit is the multi-valve port block made of stainless steel, which you can see here on the right side of the slide. And another one to mention is the business unit Semiconductor, which is a very fast growing one, as you can imagine. And here as well are multi-valve port blocks used at our customers' plants, but they are made of special kind of plastics, because here in these plants, in this area, very aggressive media is used to producing these semiconductor products. And the last business unit I want to mention is the business unit industry. And here comes the product, one of our globe valves into on the slide, which we focused on at our case study today. I will focus on this product later on a little bit more in detail. And the last business unit I want to mention is the business segment medical. So it's a small business unit. And here a typical representative of our product is a single-use valve body, which is mounted underneath electric drive of Gemu. So Gemu is not only developing and producing electric drives, but also pneumatic drives, manually driven drives, and also electromagnetic drives. In the following slide, I prepared some of representative customers of Gemu, and I clustered them with the 3 major business units of Gemu. So on the top left, you can see representative customers of our business unit industry. So here companies, for example, like Zyblin, CAESES, or Hermle could be mentioned. The companies within the business unit pharma, food, biotech should be much more familiar to you. So companies, for example, like Pfizer, like Roche, or Tetra Pak could be mentioned. And for the last business unit semiconductor, it's companies like Samsung, Infineon, or BASF. In the following slides, I want to, let's say, focus a little bit more in detail on the Gemu 534. So it's the actual valve we used for our case study here. Gemu is not only producing, let's say, or Gemu is producing different kind of globe valves. So in this slide, you can see the 4 different globe valves models Gemu is developing and producing. So on the top left, it's a kind of a standardized globe valve body. To the left, it's an angle seat globe valve body. Then there is the 2-3-way globe valve body and an angle globe valve body. And to give you more detailed picture about these products, I brought some photos for these valves. And here you again can see Gemu is not only producing, let's say, the globe valves, the bodies itself, but also the actuators. As I said before, the actual geometry we are focusing on is a globe valve with a plastic piston actuator on top, which you can see here in black, and it's pneumatically operated. The valve is available as shut-off valve, so it's either fully open or fully closed, and as well as a control valve, so you can smoothly control the opening position of the piston to, let's say, control the flow flowing through the valve. And compared to the angle seat body, you have a higher pressure loss in this globe valve body because of the sharp change of the direction of the flow, and therefore there's the need, let's say, to create the optimized design to reduce the pressure loss here in the geometry. As I said before, the Gemu 534 is used in the business unit industry, and that this business unit industry is focusing on 5 different markets. So the markets are, for example, surface finishing and chemical engineering industries. But in these areas, again, aggressive media is used, and so these valve bodies made of metal can't be used because of that aggressive media. But in the other 3 markets, the Gemu 534 is used. So it's mechanical engineering, processing industry, power generation, and environmental engineering, and industrial water treatment processes. In the end of my presentation, I want to give you, let's say, the motivation why we're using CFD-driven shape optimization, what are at the moment the restrictions, and which challenges we're facing every day in our daily work. So I want to start like this. Normally, physical systems and processes are quite complex. They are often complex, and they are influenced by a lot of input variables. So, and the relation between these input variables and the outputs, they are often not well understood. So it's kind of a black box. And we often understand our valve body like such a black box. And this valve body, as I said before, could be described by input parameters. So, and these input parameters could be the dimensions of the valve body. For example, P2 as a radius here in the lower part of the geometry. And we want to get ideas how the parameter, for example, P2 is related to the pressure loss across the valve body. And therefore, we vary the geometry in a very nice, very smooth way, and therefore try to investigate the relation between the geometric input parameters and the calculated or simulated pressure drop or velocity field as outputs. So to sum this up, in general, the main target is to investigate the relation between inputs and outputs, and therefore, of course, the usage of numerical methods is very beneficial. There's a high potential for money and time savings, and the possibility afterwards to perform numerical optimizations of the system is very nice. Yeah, in this slide you can see let's say the general workflow we're using for geometric design optimizations here at Gemu. And I will start in the top of the slide. The starting point of that workflow is the parameterization of the CAD geometry, and that's a very tricky part. I will focus on that a little bit more in detail afterwards. After that, you have to define the boundaries of your geometry, then define its design space, perform all the CFD calculations, evaluate all the results, reduce it to the most, or reduce the input parameters to the most important ones, and use these input parameters for the design optimization afterwards. And for the CFD part, a very good tool to use is SimScale, and it's very powerful. But what about the upper part, the parametric part of the CAD contour? I think a lot of people know that problem. If you're using conventional CAD tools like we do here at Gemu, for example, we are using SolidWorks, it's very difficult, let's say, to change a geometry in a kind of arbitrary way. So, for example, if you want to change the parameter P2 with a certain value, X, for example, and recreate the geometry to perform the CFD simulation afterwards with this new geometry, there's often the geometry is often not able to refresh or update. So it's not possible to use such CAD tools in a fully automated workflow like the one I presented. So therefore, we use CAESES to create the parametric CAD geometries. And with these words mentioned, I want to come to the end of my presentation and give a special thanks to guys from SimScale and Friendship Systems. It was an honor to work with you in this special case study. And now I want to hand over to Mattia.
Fits quite well with what I want to talk about. So Marco has introduced the valve that we're looking at and the motivation behind this optimization project. And I would like to talk a little bit more about how specifically we approached it and how we set up everything and get to the results that we obtained at the end. But before we get to that, let me start with some motivation on our side here at Friendship Systems. So the target of what we're doing is automation of the design process specifically, and automation of the simulation process. And as we know, or many of us probably know, competition in the market, laws and regulations, customer requirements are driving the demand for high level of performance of engineering products. And a very good way to reach that, or maybe the only possible way to reach that, is by using optimization. And As Marco already mentioned in his presentation, optimization and automated design exploration can lead to better and designs, obviously, but they can also shorten the development times, reduce the design cycles that are needed to get to a certain result, and maybe a little undervalued point, but quite important point, is that they increase the knowledge about how the product behaves with respect to changing parameters and what their effect is on the performance measures we're looking at early in the design process, which allows us to collect a database of information that we can use to base our design decisions on. And if we want to reach this kind of process automation for simulation-driven design or CFD-driven design, we basically need three components. We need the simulation tool that will provide us the performance information we're interested in, and that's basically taken care of by SimScale in this case, as we've seen. We will need a driver of the optimization process, which basically controls the whole process and provides the algorithms and strategies that we need to run the optimization or a design exploration. And we need a suitable CAD tool that is able to produce the different geometry variants. And basically our tool CAESES that we develop here at Friendship Systems is taking care of these final 2 points. And as I mentioned here, the CAD component is a quite important part of our tool CAESES. And Marco answered this question partially already, but many people we're dealing with ask themselves, why would they need another CAD system? Every company is using a CAD system nowadays. And in our experience, when trying to set up such an automated process, many of our customers experience most of the bottlenecks in the handling of the geometry. So, and this is the point that Marco mentioned already, when using these kind of, I'll call them traditional CAD systems, geometry variation is often difficult or prone to failure. So you change parameters, the geometry update breaks down. But there are also other points like constraints. Often when we want to optimize a certain geometry, we're dealing with a set of constraints that can come from manufacturing, for example, or packaging. And of course, we would like our optimization result, the geometry in the end, to fulfill these constraints so that we have something that is feasible to manufacture and feasible to use. So that's also a point that is often not so easy to take into account, all these different constraints that we have on the geometry. Sometimes you also have a certain organizational subdivision within a company that simulation engineers that are taking care of the simulation are not necessarily the ones who are handling the CAD system and creating geometries, so they might need depend on the CAD department to provide these geometry variants. And finally, here, as the quality of the CAD model might not be suitable for simulation. So what comes out of the CAD system does not fulfill the requirements that you have in your simulation tool, or rather the meshing process that comes before the actual simulation. And of course, if we want to automate the process, we need to make sure that every geometry we generate is able to fulfill these requirements directly and automatically. And basically, these are the points that we are focusing on with our tool CAESES. So it's not necessarily a replacement for other CAD systems, but rather an additional system that is very highly specialized on the process of geometry variation within the context of simulation-driven optimization. So let's look at the different components that make up CAESES. And the first one is the CAD environment. I've talked about that already a little bit. So we have a focus here on creating smart geometry models that are efficiently parameterized, which means give us a lot of flexibility in changing the geometry. But of course, we're trying to use as few parameters as possible to reduce our effort for optimization. We want geometries that are simulation ready, can be handled directly by meshing and simulation. 100% robust geometry variations so that we are able to generate all the variants that we want, and constraint management. And our focus, or maybe what we're specialized on a little bit, is these kind of more complex geometries that have often free-formed shapes that are typically even more difficult to handle and parameterize with traditional CAD systems. And you can see some examples here on the side. So staying with the CAD environment in CAESES, let's take a look at how we handled the CAD-related tasks specifically for this globe valve that we wanted to optimize for the modeling process. You can see here the user interface of CAESES with the model of the valve geometry. And what we started with was an original CAD geometry, which was provided by Gemu, which you can see in the picture. And the first step was to extract the fluid domain, which is basically the part that we are simulating, and with the goal of remodeling that part with a parametric model that we can use for optimization. And that worked in such a way that we defined the inlet part of the valve and the outlet part of the valve by these profiles or contours. And on the inlet and the outlet side, we have what we call long contour, that's the blue one, and a short contour, the green ones respectively. They are controlled by a couple of control points with different parameters we'll see later. And then in the next step, basically we take a cross section that we sweep along these contours, as you can see here in the side view or in perspective here. So we have a circular cross section, which can also be elliptical with controlled by an additional parameter. And basically we sweep a point along the short contour and we sweep a point along the long contour and connect these 2 points with a circle or an ellipse, and that controls the kind of the vertical axis of the ellipse, and the horizontal axis is controlled by an aspect ratio parameter so that we can make these cross sections wider to the side. And this gives us surfaces. Basically, if we take these cross sections, sweep them along, then we obtain our surfaces for the inlet and the outlet part of the valve. And we add some additional surfaces here for the valve seat and this kind of housing for the plug at the top, and intersect them with our inlet and outlet surfaces. Additionally, at the top here, we have this large fillet to kind of smooth out the geometry there. And then we add the plug to the geometry, which in this case is just taken from the imported geometry, so that one's not parameterized here in this case. And then we have the geometry for our fluid volume in the valve, and for the CFD computations, we extended the inlet and outlet upstream and downstream, so that we have kind of a piece of duct where the flow can be fully develop, and then we have another piece at the outlet for evaluations. Okay, this kind of concludes the geometry modeling part, and we can move over to the next block, which is the automation of our external simulation tool, obviously SimScale in this case, to simulate our valve geometry. And in CAESES, this is handled with a generic interface. So it's not a dedicated interface for a specific solver, but it's rather, as I said, a generic interface, which is able to couple to arbitrary external analysis tools. And basically in this interface, we define the data exchange between cases and the external tool. So all the input files that are needed and all the output files from the simulation that we want to load into cases after the process has finished. And if we look at that in a bit more detail, in the upper half of this interface, we define the input files, so what is exported from cases. Obviously, we have the geometry that is exported in a suitable format for our external tool. It can be a CAD format like STEP, IGES, Parasolid, or it can be a discretized format like STL or other things like that. We have additional input files in the other field here, which I will talk about a bit more on the next slide. And then in the bottom half of our interface, we define all the result files, output files of our solver that we want to load into cases. It can be complete files, like a complete flow field that we can use to do some post-processing in cases, can also be externally generated screenshots, things like that. So basically all things we want to collect for our design variants within cases. And in the second field here at the bottom, we more specifically define certain files where we want to extract specific values from, and these are typically values that we would use as an objective or constraint during the optimization process. In this case, for the valve, it is the parameter KV, the flow coefficient that characterizes the performance of the valve. So this case here, where we're connecting to SimScale, is maybe a bit special compared to what other customers of us are doing, and this is something that we worked on with SimScale, since they provided this API that can be used for external tools to connect to the SimScale simulation platform. And the special thing here is that we have CAESES as the optimization system running on your local workstation, while, as we've heard, SimScale is running in the cloud. And so it means that the geometry and script files that we are exporting from CAESES are loaded into the cloud onto the SimScale simulation platform. The computation is performed there, and the result file is then downloaded from the internet, from the cloud to your local workstation again after the computation has finished. And as I said, we connect to the SimScale API, and this is done through a Python script. We see a part of it here in the picture on the right. And basically, this script is set up once at the beginning to have all the computation set up for our case. And then we're basically just using the same Python script for every variant that we're generating. So basically, we repeat the whole process of assigning all the settings, running meshing, running computation, extracting results in the same way for each variant. And additionally, I mentioned here that you can also parameterize values within these script files in CAESES, so that you could actually also run optimizations with a combination of geometry parameters and simulation parameters if that is needed. For the CFD setup, just very briefly, we have water as a fluid. We have a 1 bar pressure drop defined across the valve between inlet and outlet. And we're using simply fully automated mesh settings, just relatively basic setup, nothing fancy. And the first test we did to test the connection between CAESES and SimScale was by running an automated valve curve. So what a valve curve is, if you're not familiar with it, is basically we take the plug of the valve or piston or whatever you want to call it, and from a fully closed position and lift it up to a fully open position with several steps in between, and evaluate the flow coefficient through the valve for all of these positions, and then we obtain a curve like that here for the normalized plug position and the flow coefficient Kv. And we can see here this is a so-called quick opening valve where you have a steep slope of flow coefficient development, so to say, at the beginning. So this basically proved that the connection between the two tools work. We are able to launch computations in an automated way from within CAESES. Everything is fine and set up so that we can go to the next step in the process, which is the actual optimization. And this is the third component that is available within CAESES, the optimization environment that provides all the necessary tools to run an optimization or parameter study, which means all the algorithms that you need for that, but also ancillary tools like data management. So we generate a lot of geometry simulation data that we need to handle and manage in a good way, as well as the post-processing tools to look at your results and evaluate what has happened there and basically make your decisions in the end. So if we go back to our globe valve case, here are the parameters that we selected for our first optimization study. We have 4 parameters that control the inlet, the long contour of the inlet part of the valve. Yeah, so you can see here the blue contour. We have different parameters here that move the distance here of this point, the position, and streamwise direction, and the same for this other control point. We have 2 more parameters for the short contour of the inlet part, and 4 parameters on the outlet long contour. So basically the same parameters as for the inlet part, just up there. And 2 parameters for the short contour of the outlet. And then we have some additional parameters that control the shape of the cross sections. As I said, these cross sections are, so say, initially circular, but we can also make them elliptical by controlling the aspect ratio between the vertical and horizontal axis of the ellipse. And here we have 2 parameters that control the distribution of this aspect ratio in streamwise direction here for the inlet part. Basically here the maximum value of the aspect ratio, and here the position streamwise where we have that maximum value, and basically the same thing again for the outlet part of the valve. So in total we have 16 parameters, and you can see here in this animation how the different geometry variants look like if we change all of these parameters in a combined way. Then we get a multitude of different shapes. So let's look at the results, or rather how we came to those results. We started the whole process by doing a DOE, a design of experiments, which is basically an exploration of the design space with 120 designs. So this basically probes our design space in all its different regions to give a first idea where what are the correlations between the parameters and the geometry parameters and the output parameters. And based on the result on this database that we generated with the DOE, we generated a so-called response surface, which is a surrogate model that basically allows us to interpolate the result within our design space. And then on this response surface, we can run an optimization. And the result is the results for the optimization process are taken from the surrogate model, but every now and then we run a CFD computation again to double check our results from the surrogate and see how accurate they are, and then we can take in those results to refine our surrogate model, and then until we are converged until up to a certain optimum within the design space. And that ran with another 50 designs that were computed by CFD. And as a result, we got the shape, the blue shape that you can see here on the right. So the silver shape is the original valve, and the blue shape is the optimized valve from this first optimization study. And we reach an improvement in the flow coefficient of approximately 6.5%, which was already a nice result. And fine, in the next phase, we wanted to see if we can push this further. So we ran a second optimization study. We retained 8 of the original parameters that were used in the first optimization study. So basically, we selected the ones where we could see from the correlation plots that they have the biggest influence on our flow coefficient, and we discarded the 8 remaining parameters that had the less pronounced influence on our flow coefficient. These 8 parameters, and then we added some new parameters, 2 new parameters for the long contours on the outlet and on the inlet. You can see here in the animations. And we added 2 parameters for an additional control of the cross sections. So if you remember what I told you before, that if we look here, we sweep these cross sections along these contours. And the parameters we introduced here basically control the speed in which we sweep along the long blue contours. And this would look like this. So you can see that the cross sections move much quicker to the end of the contour, and that also creates some quite dramatic changes in the geometry. So for the second optimization study, we had 12 parameters in total. Again, you can see an combined variation here in the animation. And as a result, here we, after running a response surface optimization again, so in this case, we started directly the response surface optimization, which will create its initial database then automatically, and then run this response surface optimization with 160 designs. And then we followed that up by a small local optimization. So we took the result of the response surface optimization, the final design from there, and starting from that design, we did a local search with just 2 parameters, which are these sweeping speed parameters that I explained just before. And as a result, we got a further improvement of the flow coefficient. And in the end, we have an improvement of about 9% compared to the baseline that we started with. And here we have, to conclude, basically a comparison of these different designs that we generated. The silver one is the baseline geometry, the blue one is the optimization, the result from the first optimization study, and the green one, the result from the second optimization study. And yeah, I think it's interesting to see that the result of the 2 optimization studies are quite different, I think, even though they have maybe some similar characteristics, like here the wider inlet, but also some quite different shapes, like this radius here at the bottom, for example, looks quite different. And yeah, I think the result were very good, and we could prove that this whole process works and that we're able to obtain good results with it. And that concludes my presentation. Thank you very much, and I'll give back to John for a wrap up.
Really interesting webinar so far, even though I'm part of it. So thank you very much, Mattia and Marco, really cool. We have a whole page worth of questions, which we are never going to have time for, but I'll try and get through a few. Actually, let's put our videos back on too. So just to quickly summarize, we've looked at essentially how to leverage SimScale and the power of the cloud in conjunction with CAESES to optimize a valve that Gemu, one of our customers, provided. Really cool, really interesting. Thank you, both of you, most definitely. And let's try to answer some of these questions. We really have a lot. I think I would start with asking, I think this is a question for you, Marco. So the results of the optimization look promising. I think they look really super interesting. But what about the manufacturability of the geometry? So maybe that's a little bit to both of you. Mattia, how do you guarantee that? And Marco, how do you then manufacture a shape that could end up being quite organic?
Yeah, I mean, maybe I can start. It's a very important question, of course, because in the end, you have to, let's say, produce the geometry. If you want to sell it, if our customers want to use it, we have to manufacture it. And therefore, during the creation of the geometry in CAESES, we fixed some of the geometries, some of the important geometries to, let's say, replace the new geometry, the new valves, with the existing ones in the plant. So the inlet and outlet are fixed, and also the seat is fixed. And I also, with the final result, I checked with the guys from the manufacturing department here at Gemu, and they told me, because I mean, of course, the geometries look different, but in general, it's the same contour and it's a casted part, and therefore the valve body could be manufactured.
Yeah, maybe to add to that, since I didn't work on this case myself, I don't know what my colleagues specifically set up for this case study as a constraint, but I can speak a bit generally about taking in manufacturing constraints into the parametric model. And we have several tools and, let's say, routines and ways to check certain properties of the geometry for certain parameters that are connected to the manufacturing method. And typically this involves things like wall thicknesses. So here for a valve, I remember we had another case with a valve where we check basically the distance between the contours of the inlet and the outlet part, so that we have a certain minimum remaining wall thickness between inlet and outlet. Or we might check things like radii or angles of the geometry or curvatures, things like that. And typically this is something that we would need, or the designer that is using CAESES would need as an input. So I don't know, if you have a cast part, you have, for example, to add certain draft angles so that you can separate the mold or things like that. And then with this knowledge, you can use the tools that are available to check for these properties on the geometry.
Cool, thanks both of you. Could I ask you something additional, Mattia? Probably just needs a yes or no, I think. But one question was, can we add more constraints or more parameterized values? So do we hit a limit within CAESES, or could you parameterize it more if you wanted to?
You could parameterize it more, yes, for sure. I think we made a certain selection here for this case of, let's say, reasonable parameters. But yeah, you can always add more. You can also get maybe even more experimental with the shape. actually hear the results. We saw that there was some room with some of the parameters to create some more unconventional shapes, which actually wasn't followed by the optimization in the end. But you could also make it more, let's say, strange and experimental in shape.
Cool, thanks. That's what I love about this, though, because it's past what our minds can even think of, right? And it does way more. So really cool. Thanks. A couple of other questions. How much does this cost? A question for you and I, probably, Mattia. I think each run costs something in the realm of like €2 or $2, right? Something of that order of magnitude. And then we can just multiply that out, right? So maybe a few hundred in the end to run all of the different simulations. And then CAESES basically pulls from all of those, right?
Right. And yeah, for the CAESES part, I think it's not so easy to answer the question. We have many different license models that can go from a basically pay-as-you-use model to short-term, long-term rental, perpetual licenses, and then we also have some differences based on the kind of company we're dealing with and so on. So yeah, if someone is interested in that, feel free to reach out to me and we can work out this suitable model.
Cool. Looking at the number of questions, I think people are very interested in it. I'll just pick a couple more. So one is what kind of applications can be simulated in SimScale and what CAD can be imported? And I think this connects to what we're doing here too. So you can run many different applications. A lot of the things like structural and thermal and CFD that we showed at the beginning. But it always astounds me how our customers and users dream up more and like amazingly varied ways of using simulation. So it's unbelievable what people think of and different ways to use it. And then using optimization on the top is getting quite limitless, really interesting. And we can read in any different type of CAD, so native formats, STL, or anything from the major CAD systems as well. We've got 5 minutes. I think maybe we can kind of combine on this, and I'd like to maybe contribute a bit too. So how easy is it to get started with SimScale's API? It'd be interesting for you, Mattia. For me, I'm not into programming, so for me, it's probably quite challenging. But from what I've seen of other users who know Python really well, they've picked it up really quickly. Do you have a point of view, Mattia?
I do have a point of view. I mean, in this case, it was very easy for us because the Python script for this case, which was actually provided by your colleagues, John, and all we had to do was take in the Python script and then automate it. So in this sense, it was quite easy. But I understand your point of view that, of course, there might be a certain barrier if you're not so much into programming and you would have to write that Python script completely by yourself. And I think maybe an outlook into the future and hope if there is interest in this is that you could set up a case in the SimScale platform in the user interface of SimScale and auto-generate basically the Python code for that setup. That would be kind of the ideal case from my point of view, because I mean, there is users who are familiar with Python and they like programming and this kind of things, but some are not so much. So it's always good to provide an easy access point.
Cool. Yeah, I agree. I think we can do that now, by the way. But yeah, that looking into the future, that would be the next step, right? Making it really simple and easy to use. Exactly. Okay, still many more questions. Does the simulation prevent cavitation? We can simulate cavitation, right? And then I'm sure that you could use your software to minimize or reduce cavitation out of the simulation. I guess that would make total sense.
Yeah.
Yeah. What else is there? I think we've probably reached most of the major questions. I think that I think that's okay. So I would kind of wrap up then, just to say a couple of things that we will share this PowerPoint afterwards. and you'll get a recording link that you'll be able to view if you'd like to. You can access SimScale now as well if you would choose to. So you can use the link to reach or access this simulation that we ran. You can request a demo or just get started, and an application engineer can reach out to you to give you some help. And I'd just like to say it was very, very interesting for me. I'm really excited to see people start using this and see what comes of it in the future. And thank you very much, Mattia. Thank you very much, Marco. I look forward to working with you more. And thanks, everyone, for joining. See you next time.
Thank you as well.
Thank you very much.
Maybe just one final word. Sorry. The same applies for CAESES as well. You can download a CAESES from our website, caeses.com, and you can register for a trial license, so you can test the software by yourself. And there's tutorials and so on to get you started. So
cool.
Thanks.
Thank you. Any last words, Marco?
Not from my side. Thank you very much, guys.
Cool. Thank you. Next time.
See you. Bye-bye.
Bye.